In this lecture, we are going to begin discussions on velocity analysis of mechanisms. So, first I will define what is the velocity analysis problem, then we will look at some elementary geometric concepts in velocity analysis, based on which we are going to discuss something called instantaneous center of rotation of a body, of a rigid body. So, to give you an overview, so we are going to first define the velocity analysis problem, look at some geometric concepts as I mentioned, which will lead us to this concept of instantaneous center of rotation. So, what is the velocity analysis problem? As you know, a mechanism transforms actuator velocity inputs. So, there can be multiple actuators, and these actuators provide velocity inputs. You can think of actuators providing velocity inputs, which are transformed by the mechanism to the output link. So, the velocity analysis problem is to find out the velocity input output relations. Let us consider this example of this transfer device. Here we have this actuator. As we have seen before, this is a constraint mechanism with 1 degree of freedom. So, this is the actuator. It is a prismatic actuator which will expand, and it will take this chair from the sitting position to a standing position. Now, the problem is, if I want to have a certain velocity of transfer, then what should be the expansion rate of this actuator? So, rate of change of length of this actuator, how does it relate to the rate of movement of the chair from the sitting to the standing position? Now, when the person is near about the standing position, then the velocity should be less, so that he is not pushed forward. So, we need to control the velocity of the rate of expansion of the prismatic actuator. Here is another example of the landing gear mechanism of an aircraft. So, if I want to know at what rate must this actuator, this hydraulic actuator expand, so that I have a certain rate of retraction of the wheel. So, for constraint mechanisms, we are going to look at the velocity analysis problem. We are going to start with constraint mechanisms. Now, there are two problems in velocity analysis as in the displacement analysis. So, the forward velocity analysis problem states that given the actuator rates, find the output velocity, velocity of the output link. The inverse problem is about finding out the actuator rates given a specified output velocity. For example, in this transfer device, if I am specified a certain rate of upward movement, which might also change with the configuration of the chair. So, it might also change with the configuration of the chair. So, how do I control the actuator expansion rate? So, how should I specify the actuator expansion rate? So, that is the inverse problem. In the case of robot velocity analysis, the problem is a little more complicated. The reason being, in robots, as we know, the degree of freedom is 2 or higher. So, therefore, the end effector velocity direction decides the path of the end effector, because as you know that the path on which the end effector moves, the velocity must be tangent to that path. So, therefore, if you want to have a certain path, you must also have a certain velocity direction at each point of the path. So, here we have this forward problem which in which we are given the actuator rates, which may be angular rates or may be expansion rate of a prismatic actuator, and we have to find out the path velocity, that means the velocity at every point on the path, which of course will be tangent to the path. The inverse problem, we are given the path velocity, which means we are given the tangent velocities at every point on the path. We have to find out the actuator rates which can realize that velocity, and hence it can also realize that path. So, this is also a path planning problem. So, this is intimately connected with the path planning problem. So, for example, in this excavator, if I want to move it on a certain path, I must have the velocity is defined tangent to the path. So, these are the velocity vectors. At each point we have such a velocity vector which must be tangent to the path. So, suppose at this point if I want to have this velocity vector, what should be the expansion rates of these two actuators? Or the forward problem is given the actuator rates, what is the velocity on the path? So, either way you can look at this problem. Similarly, for this parallel kinematic machine, suppose I want to have this path, then I must specify the velocities, something like this on that path, and corresponding to these velocities I can find out what should be the expansion rate of the 3 prismatic actuators. So, that will realize this path. So, let us plan our discussions on velocity analysis. So, we will start with constraint mechanisms. We will look at some geometric concepts in this lecture. In subsequent lectures, we are going to study the analytical velocity relations for constraint mechanisms. After that, we are going to look at open chain robot mechanisms, and finally closed chain robot mechanisms. So, we will start off with some geometric concepts on velocity distribution on a planar rigid body. So, I have drawn out for you a body which is assumed to be a rigid body, a planar rigid body, and this can move only on the plane of the paper. Let us look at what we can say about the velocity distribution on the body, which means when this body moves, what can I say about the velocities of different points of the body. So, here I have marked out for you 2 points A and B. Suppose the velocity of point A is V A. If I ask this question, is there any restriction or constraint on the velocity of point B? So, point B is here. Is there any constraint on the velocity of point B? The answer is yes, and this is why it should be, because this is a rigid body. Remember, this is a rigid body. If I drop a perpendicular onto this line AB, which means I am projecting VA along AB. So, I get this projection vector. This red vector is the projection of VA along AB. Now, the velocity of point B in the direction of AB must remain the same, which means this must be the velocity of point B in the direction of AB. Mind you, I am not saying this should be the velocity of B. This should be the velocity of B projected along AB. Now, why this requirement? Because this body is a rigid body, therefore, distance between A and B cannot change. So, the relative velocity in this direction AB must be 0. The relative velocity V A relative to B in the direction of AB must be 0, because the distance AB must remain fixed. Therefore, if A has a velocity of this red vector along B, then B must also have this same vector along AB. So, what can be the velocity vector at B? So, it must be that whatever be the velocity at B, its projection along AB must be this red vector. So, how do I then determine that? So, if I take a direction perpendicular to the direction AB, if I take this direction perpendicular to the direction AB on the tip of this red vector, then you can very easily see that velocity of B can be any vector that must end at on this dashed line. So, this could be VB, this could be VB. So, any vector starting from B and ending on this line is a valid velocity vector for point B. So, any of these vectors are valid velocity vectors at point B, because their projection along AB is same as the projection of VA along AB. So, that the distance AB cannot change. So, this is an important concept based on the consideration that this body is a rigid body. So, let us move on. Now, let us consider a rigid body again on the plane with velocities specified V A and V B, which must satisfy of course our constraint. Let us look at that once again. So, this is the direction AB. So, the projection of VA along AB and VB along AB. So, let us see that vector. So, this and this, these two red vectors must be equal, and they are equal to the accuracy of my drawing. So, V and VB are valid velocity vectors of points A and B. Now, consider another point C, as I have shown here. I would like to find out the velocity of point C given the velocities of point A and B. So, can I do that? Remember, using the same constraint that the distance AC cannot change and distance CB cannot change, what I must do is I must drop perpendiculars. I must project VA along AC, VB along BC. Look at these projection vectors. So, this is the projection of VA along AC. This is the projection of VB along BC. So, therefore, C along the direction V along the direction CB must have this velocity. Once again, please remember, this blue vector that I have drawn at C is only the velocity of C in the direction CB, it is not the velocity of point C. Similarly, velocity of point C in the direction AC must be this red vector. So, I have these two projection vectors. Now, I have to locate or find out velocity of point C. So, remember what are the constraints on velocity of point C? Whatever be the velocity of point C, its projection along CB must be the blue vector at C, and its projection along AC must be the red vector that I have drawn at C. So, since these are projection vectors, so I must draw perpendiculars to these directions, and these two perpendiculars meet at this point. So, therefore, these are perpendiculars. So, therefore, the velocity of point C must be this. Why it must be this? Because its projection along CB is the blue vector, as you can see very easily, and its projection along AC is the red vector, as you can see. So, this black vector must be the velocity of point C. So, please remember that when I am given the projections along two directions of the velocity vector of a point, then to find out the actual velocity vector, I must draw perpendiculars on the heads of these projection vectors. Wherever these perpendiculars intersect, that point joined with the point, here it is C, gives us the velocity of point C. The reason is clear. This black vector must have projection projection along AC must be the red vector and projection along CB must be the blue vector. So, we have this construction. Let us move on. Again, I have chosen another point C such that the angle that BC makes with the velocity VB is 90 degree, as you can see here. I want to find out the velocity of point C. So, I proceed as we have done. So, I project VA, that means I drop a perpendicular on AC, and this is the projection of VA along AC. So, C must have the same velocity along AC. So, this must be the velocity of C along AC. Now, what should be the velocity of C along CB? It must be the projection of VB along CB. Since VB is perpendicular to CB, so therefore, projection is 0. Now, because this is 0, it means that point C cannot move or does not have any velocity along CB. So, point C does not have any velocity along CB, it cannot have any velocity along CB. So, now how do I find out the velocity of point C? So, as before, I must first draw perpendicular to the direction AC. Now, since C does not have any velocity along BC, so that vector is exactly this point C, the vector along CB is exactly 0. So, it is this point C itself. So, if I consider that I have to draw perpendicular to the direction CB, it must be through the point C. Because the velocity vector of C along CB, the projection of velocity of C along CB is 0. So, that velocity along CB is the point C itself. So, if I have to draw perpendicular to that vector, it must be through the point C and perpendicular to CB, which I have drawn. So, therefore, my velocity of point C must be this. This must be the velocity of point C, as you can very easily realize that VC has a projection of this red vector along AC and VC has 0 projection along CB. VC has 0 projection along CB, VC has the projection of that red vector along AC. So, this must be the velocity of point C. Now, this construction brings us to this important or interesting question, that what would happen if I had taken the point C which lies on the common perpendiculars of both VB and VA. So, that is the question we are going to address next. Okay. So, here I have two cases. Let me start with case 1. So, if I ask this question, that let me take a direction perpendicular to V b and a direction perpendicular to V a and locate my point C here on the intersection of these two perpendiculars. So, these are perpendiculars. I am locating point C on the intersection at the intersection of the two perpendiculars to V a and V b. Now, what is the velocity of point C? From the previous constructions, it is very easy to see that velocity of point C must be 0. Velocity of point C must be 0. Why? Because along B C there is no projection of V b, therefore, the velocity of C along C b must be 0. The velocity of C along A C also must be 0, because V a also does not have any projection along A C. So, therefore, velocity of C along two directions, projection of the actual velocity of C along two directions is 0. These two directions are non-collinear. So, therefore, the velocity of C must be 0. This is known as the instantaneous center of velocity or instantaneous center of rotation. This is the instantaneous center of rotation. So, the idea is that at this instant with this velocity distribution, that means velocity of point A given by V a and velocity of point B given by V b, and hence since these two velocities are specified, velocity of any other point is actually specified. So, the whole motion of this body is specified. So, at such an instant you can imagine that this point C is kind of hinged to the ground, because its velocity is 0 at this instant. So, as if the whole body is rotating about point C. That is the idea of instantaneous center of rotation. But remember, this is at this instant, that is why it is called instantaneous center. At this instant, next instant the velocities might change and C will go to some other point, but still there will be a point C which is the instantaneous center of rotation. The velocity at that point is 0, and hence it may be assumed that at that instant it is kind of hinged to the ground. Now, we come to case 2. The velocities of the 2 points A and B might be like this. I can of course draw a common perpendicular direction, but beyond this I do not have a clue how to locate C. But then remember, if some point is to be hinged, which is the instantaneous center, then the velocities of these points A and B must be proportional to the distance from that point. So, therefore, if I locate it this way, this point is C, and you may assume that this point is hinged. This is the instantaneous center of rotation when the velocity distribution of 2 points A and B are as shown in case 2. you can see that velocity b is proportional to b c and velocity of a is proportional to c a, and that is why it is increasing linearly with that distance, because the angular velocity of this body is something which is fixed. So, that brings us to the concept of angular velocity. Angular velocity. So, here I have drawn out for you the instantaneous centers of rotation for the two cases, and we have this angular velocity. Now, how do I define angular velocity? Angular velocity is defined as V a by C a. So, the C a is the radius vector. So, you know that omega cross C a must be V a, and similarly omega cross C b must be V b. So, therefore, this must also be equal to V b by C b, and this is valid for both the cases that I have shown you. So, you need to remember how to relate the velocities, say the center of rotation, with the angular velocity of the body or the angular speed of the body. Now, this we are going to use. So, this is how we define the angular velocity or angular speed of the body. How do we relate the angular speed with the center of rotation? So, once we can locate the center of rotation of a body, then we can find out the angular speed of that body. So, to summarize, we have looked at the velocity analysis problem, we have looked at some geometrical concepts in velocity analysis, and finally, we have come to the concept of instantaneous center of rotation of a rigid body. So, with that I conclude this lecture.